Okay, perfect. So today's workshop is titled The Statistical Analysis, Inferential Statistics and Regression Analysis. My name is Kokezo Pila and I will be your moderator for today's session. And firstly, I would like to notify you, as I've already mentioned, that the session is being recorded and I've already started the recording. And I would like to start off by thanking our attendees for taking their time to join us today in this session. And most importantly, I would like to thank our presenter, Ms. Elsabe Smith, for her effort with preparing and giving this presentation. Before I can then officially introduce Ms. Elsabe Smith to you, I would like to go over some housekeeping rules and some of the important information that you need to take note of. So for the housekeeping rules, if you do have questions during the presentation, please raise your hand if you would like to speak, or you can type your question on the chat box. I will then indicate to the presenter to address your question. And as I've already mentioned, the session is being recorded and the presentation slides together with the recording will be uploaded on our module community and RCDMS before the end of the week. And also there is a feedback survey that will be sent out on the chat during the session. Please may we request that you fill the survey out for us to gain some insight on whether this workshop was useful and how we can improve in the future. And you can also suggest some of the topics that you would like for us to cover in future that will be useful to you. And also by filling out the survey, it ensures that you receive a certificate of attendance. And just a reminder that everyone needs to make sure that they are registered on our RCTMS, which is the RCT management system, so that you can get the communication, all our communication from that platform. And without further ado, I will then introduce our facilitator, Miss Elsabe Smith, by reading out her bio. So Miss Elsabe Smith started her career as a statistician at the Rand Afrikaans University in 1994, completing a BSc in mathematics and mathematical statistics. While studying at RAU, Miss Elsabe worked at the Statistical Consultation Services, StatCon, first as a student assistant and later as a data analyst. After graduating, Ms. Elsabe moved to Cape Town and worked as a statistician in market research for 5 years. During this time, she completed her honors in mathematical statistics at Stellenbosch. Ms. Elsabe then enrolled at UNISA for a postgraduate certificate in education. She worked as an educator in England for a short period and spent some time traveling through Europe. Upon her return to South Africa, Ms. Elsabe joined another market research company as a senior statistician for 3 years while studying for a MSc in mathematical statistics at Wits. From 2009 to 2016, Ms. Elsabe worked as a senior tutor in the statistics department at Wits University, where she taught statistics services courses to students in commerce and humanities. Since 2017, Ms. Elsabe has been a lecturer in the statistics department at the University of Johannesburg, where her statistics journey began. So without further ado, I will then hand over to our facilitator, Ms. Elsabe Smith. Just to get confirmation from you, Ms. Smith, would you like to take questions during the session, or would you rather reserve these questions for the end, at the end of the session during the Q&A?
Thank you, Kokezo. I don't mind if there are questions during the session, if I have to clarify something. So by all means, there is a question, maybe a short question, maybe the longer in-depth questions we can leave for later. But if there's some clarification required as I go through the presentation, by all means, stop and ask.
Okay, thank you for that. So yes, the participants, you can reserve the long questions for later, and if you need clarity during the workshop, then you can raise the questions, and I will indicate either type them on the chat, or you can raise your hand. We will then unmute you, and then you can ask your question. Thank you very much. Over to you, Ms. Smith.
Well, thank you very much, and welcome everybody. Let me just share my screen so that I can go to my PowerPoint presentation. Right. Okay, presentation mode will work. There we go, much better. I trust that everybody can see that clearly. So today's training session is about statistical analysis, inferential statistics, and regression analysis. And as I go through this, when I put it together, I thought it's not going to help if I just show you all the formula and show you how to calculate it by hand. It's more about the conceptual understanding of inferential statistics. What is behind it? How do we do it? What is the rationale for it? And what does it ultimately mean? Because as you do analysis, you are going to come across hypothesis tests. And if you understand what it's all about, well, that really helps your insight and the meaning of it. So as part of this presentation, there are two sections. The first is inferential statistics that I will introduce, as well as certain problem statements that we can address. And what's in the background of this is the sampling distribution of a statistic. Then we go into estimation and hypothesis testing, and a big thing to understand what is a p-value, because you will come across p-values when you do hypothesis tests. What exactly is it? How do we interpret it? And I'm only going to show you one actual application of this, because in inferential statistics and hypothesis testing specifically, it is a certain structure that is applied to whichever problem statement we work with. But anyway, we'll get through to that and I'll explain more. Then we look at correlation and regression analysis as an introduction, the scatter plot, the correlation analysis, the regression analysis, as well as some examples. Right, and in terms of inferential statistics, when we study, we're studying a population. Now, it's not always possible for us to get all the N units of that population and investigate them. And that's due to time or cost or accessibility constraints. Our solution to this is to randomly select a representative sample of a size n, the little n, and then we can calculate sample statistics. What is important when we select a random sample is that it represents the characteristics of the population. If we don't use proper sampling methodology for probability sampling methodology, we cannot do statistical inference. So it's really important when we design a study, now that's a whole different discussion, but when we design a study, is that we use appropriate statistical or rather sampling methodology if we want to do inferential statistics. Inferential statistical methods are then use these sample statistics that we calculate from our sample to estimate our population parameters. And the four pillars that support inferential statistics are the following. Number one, it's descriptive statistics. Now, I think you have done some basic statistics. Descriptive statistics is where I really just calculate values from my sample and it describes what is happening in my sample. Then we have probabilities, especially the normal distribution, but also other distributions. And then the concept of the sampling, or rather the sampling methods and the influence on sampling error, and the concept of a sampling distribution. Statistical inference can be performed in two ways, and it's through estimation and hypothesis testing. Before I go into any of that, I want to talk about the different problem statements. Inference made about population parameters, that inference will depend on the nature of the problem statement. When we do research, we don't start off with, oh, I'm going to do the following 10 tests. We start off with problems. And then statistics is really just a toolbox with a whole lot of tools in it. And you will use the appropriate tool to address a particular problem statement. For example, we can make inference about a single population mean, and that takes us to the one sample t-test, or inference about a single population proportion, where we use the one sample proportion test. If we have related samples, for example, if we want to test what are the test marks before an intervention and after an intervention, or blood pressure before you run a mile and after you run a mile, then we will have related samples and we can compare the pre versus post. For that, we use the dependent samples t-test. When we compare two independent groups, the means of two independent groups, for example, if I have my group of students in the class and they wrote a test and I want to know how the males are perform on average compared to the females, and then we will do an independent samples t-test. If I have multiple independent groups, 3 or more, then the independent samples t-test is not the appropriate technique because it only works with 2 independent groups. So the ANOVA, analysis of variance, is used to compare 3 or more independent groups with respect to some or other numerical variable of interest. We can also do inference about categorical data. For example, we can compare the distribution of a single categorical variable with a known distribution. That is called the chi-squared goodness of fit test. Or we can look at the association between 2 categorical variables, in which case we will do the chi-squared test of independence. Now, each of these above analyses will make distributional assumptions, and it will therefore incorporate a specific theoretical statistical distribution in its calculations. And these distributions could be the the standard normal distribution, my Z distribution, the student's T distribution, F distribution, chi-squared distribution, whatever is required for that particular problem statement or unique to that particular problem statement. And that's captured in the assumptions that we work with for the test. Right. Now, as stated before, we use sample statistics to estimate population parameters. The problem, however, is that if I draw a sample, a random sample from a population, and I calculate, let's say, the sample mean, that sample statistic that I've calculated is not necessarily exactly equal to the population parameter. And if I had drawn a different sample and do the same thing, calculate the average, then that's going to be different from the previous sample that I had. So my sample statistics will vary from sample to sample. Now, when we do inference, we are not going to go to the population. We are working with samples. So we want to evaluate the reliability of our inference for that population parameter by looking at the probability distribution of that sample statistic. This probability distribution is called the sampling distribution of that statistic. And it is possible for us to derive the parameters of a sampling distribution, which will then make it possible for us to calculate probabilities associated with a statistic and therefore have an indication of the reliability of our statistical inference. The idea behind the sampling distribution of a statistic, such as the mean, is best described through a theoretical concept, which we can only assess through simulation or mathematical theory. So bear with me on this. Let's consider a numerical random variable X for a certain population. In that population, I go out and I select a sample of size N, and I calculate the average of my variable X. Now, if I was to repeat this process an infinite number of times, what I will end up with is an infinite number of averages calculated from each of those samples. And those values will vary from sample to sample. Essentially, what we then have, theoretically, is a random variable of averages. We call this variable X bar. So X, capital X with a line on top. So it's variable X bar for a sample of size N. This variable is the sampling distribution of the mean. It essentially shows me that how the different sample means calculated from a sample of size N, from this population, is distributed. All possible samples. What is the nature of all the possible sample means that I could calculate? Of course, this is not realistic for us to calculate this. Nobody's going to go out and do an infinite number of samples. This is a theoretical exercise, but it mathematics underpinning it. Let's illustrate it a bit better. Let's say our random variable X is the height of the adult female population in South Africa. Now, let's further assume that X is approximately normally distributed with a mean of 165 centimeters and a standard deviation of 10 centimeters. This is quite a reasonable assumption in terms of height of the female population, because the majority of females will be around the average height, and then only a few females will be on the shorter end of things and a few females are taller. So this picture of the normal distribution is a reasonable representation of the shape of the distribution of this particular random variable in the population. So what we have here is the distribution of my random variable X, namely the height of the female population. If I now take a random sample of size N from this population and I calculate the average, then it is reasonable to assume that my average should be, so if the average in the truth, the reality is that it's 165, if I calculate an average, maybe I get something over here. A different sample may give me something here. So if I take another sample, sometimes I'll get exactly close to that population mean of 165, but you will agree with me that most samples that I draw from this population should yield an average round about the middle of this distribution. And only occasionally I will get something, an average that's really low or an average that's really high. But the majority will be somewhere in the middle. And what we will have then from this is that it creates a shape. The distribution of all possible sample means creates its own shape. I'm sorry, I can't draw this very nicely by a free hand. It's supposed to be more of a smooth curve here. This then yields the distribution that we called X bar for a sample of n. So this is the distribution of the average height calculated from a sample of size n. We can derive this theoretical distribution of the sampling distribution of a statistic, such as the sample mean, as well as its parameters. It all depends on what the original shape was of the variable of interest. If the original variable is normally distributed, my sample mean will also be normally distributed. Let me go back to my picture. I know this picture is not nice and normal, but you can see it's that approximate shape, that bell-shaped curve, which is also normally distributed. But what if my original variable is not normally distributed to begin with, or I actually have no assumption, no clue of what that distribution is? Then we have something in statistics called the central limit theorem. It's a limit theorem that tells us that if I have enough information, the distribution of my sample mean will also be normal. It will also take on that bell-shaped curve. And for the sampling distribution, we can derive the mean and the variance. The mean of the sampling distribution is just equal to the mean of the original variable, and the variance of the sampling distribution depends on the spread of my original variable as well as the sample size that I am using. And then the standard deviation of a sampling distribution is referred to the standard error. So I'm sure you have seen when you look at some output from my hypothesis test, it talks about the SE, the standard error. Well, that is just the standard deviation of my sampling distribution of a statistic. Before I move on, let me just summarize this very quickly and why are we doing this. The whole idea of a sampling distribution is if I have this distribution of X bar, if I know what that distribution is, and I observe a sample mean in reality, I can compare it to this distribution and see, is it one of the common outcomes or is it unusual? Is it one in the tail areas? So we know how good our estimate is based on our derivation of our sampling distribution, and that forms the basis of statistical inference. We now turn to statistical inference. As I said, it can be done through estimation and hypothesis testing. So estimation, when we estimate the parameter, we calculate a point estimate as well as a confidence interval estimate from our sample. Now, a point estimate is simply a single number calculated from the sample, which estimates the value of the population parameter. In other words, if I want to estimate what is happening in the population on average, so I want to estimate the population mean, mu, I will simply go to my data and calculate the average of that random variable in my sample and say that that is the point estimate of my population parameter. A confidence interval estimate incorporates the sampling variability. In other words, it's based on that sampling distribution, and it estimates an interval within which the population parameter will lie with a certain level of confidence. What it gives us is a range of values that are all plausible estimates of a population parameter. Instead of just a single value, it gives me a range of plausible estimates. In addition to that, it expresses the level of confidence we have in our estimate. We use 90% or more, and this is referred to as the 1 minus alpha % confidence interval. So the 1 minus alpha refers to my confidence. So it's 90% typically, 90%, 95%, or 99% confident. So this alpha is just the complement of my confidence, and that is the error. I'll talk a little bit more about that in a moment. So as I said, common choices are 90, 95, or 99%. So the 1 minus alpha could be described as the proportion of samples that will yield this confidence interval that includes the population parameter of interest. Whereas the alpha, the error, could be described as that proportion of samples that do not yield such a confidence interval that includes the population parameter of interest. The structure of a confidence interval is as follows. It always consists of an upper and lower bound calculated from something we call the margin of error. And that margin of error is just the standard error. Remember, the standard error was just the measure of spread of my sampling distribution. So my standard deviation of the sampling distribution. So my margin of error is my standard error of the estimate multiplied by a critical value from the statistical distribution associated with the test. And through that critical value, we incorporate the required level of confidence. So my structure is always like this. A 1 minus alpha % confidence interval is my point estimate plus or minus the critical value times standard error. In other words, it's the point estimate plus or minus the margin of error. So in terms of the structure, I will have a point estimate, let's say the mean, so that's X bar, and then I will create an interval around it, and the distance from the point estimate to the lower bound and the distance to the upper bound is just the length of my margin of error. So it's the plus or minus. How I interpret this is, for example, a 95% confidence interval for the mean. We will say we are 95% confident that the true population mean is inside the calculated confidence interval. For example, if I now estimate, so I make the assumption about the height of the female population. Perhaps we don't know what the assumption about the mean is. And let's say we calculate a confidence interval that goes from 163 up to 170. And let's say this is my 95% confidence interval. I will then say I am 95% confident that the average height of the female population is somewhere between 163 and 170 centimeter. That is how I will interpret the confidence interval. And that is estimation. We then turn to hypothesis testing. Hypothesis testing is a very rigid process that uses sample data to test statements made about unknown population parameters. These statements about the behavior of my parameter that I'm on a test, this contradicts what is assumed to be true about the parameter to begin with. So when we do hypothesis testing, we start off with an assumption. We need to start somewhere. We start off with an assumption, and then we collect information to see, can I contradict that assumption? So that sample information is then used to see if there's evidence for the statement I want to test. Now, the note I'm making here is that it's not possible to prove something to be true, but it is definitely possible to prove something to be false just by finding something to contradict it. Right. As an example, think of this. I'm not a lawyer, but I've watched a lot of courtroom dramas, and they always say you're innocent until proven guilty. So anybody that goes to court, there is this initial starting point assumption of innocent until proven guilty. We then collect information to see, is there any evidence of guilt? But at the end of the day, we can never prove 100% of somebody is innocent, but find me enough evidence to contradict that, and we've shown or proven to a reasonable level, we can prove guilt, but also not 100%. There's always a chance of making a mistake. And that's all part of the hypothesis testing process to try and control for that error that we can potentially make. There are two ways in which we approach hypothesis testing, what I call the traditional approach and the p-value approach. The traditional approach is the pen and paper approach that was developed many years ago. The p-value approach is essentially the traditional approach, but made simpler because the computer is doing all of it and yields a p-value that is very easy to interpret. The concept of hypothesis testing can be described as follows. First of all, Say we want to test hypotheses about a single population mean. We start with an assumption about that population mean. In other words, what we assume to be true to begin with. This is like saying, I'm assuming innocent until proven otherwise. Based on that assumption, we derive the sampling distribution of the mean. We will then sample data to see if there's any evidence in the data that contradicts our original assumption about the mean. To do this, we calculate the average from the sample, and we compare that average with my theoretical sampling distribution of the mean. If our assumption is correct, then we would expect to get a sample mean that is close to the center of the sampling distribution. For example, if this is the distribution of the mean for a sample of size n, and it is centered at mu, if my assumption, my original assumption, because remember my original assumption, this distribution is the distribution under the assumption that the null hypothesis is true. I'm assuming that the mean is normally distributed and it's centered at the value mu. If I then observe a sample and I observe an average somewhere around here, well, that shows that maybe my original assumption is true. But if I observe something over here, that's quite far away from what would have happened. A typical outcome means that the average should be somewhere here in the middle. Observing an average so far out in the tail areas is quite unusual, given our original assumption. There are only 3 reasons for observing such an unusual outcome. The one is that I've done incorrect sampling methodology, and I therefore introduced bias in our estimate. So let's go back to doing inference about the height of the female population. If I assume to begin with that the average height is 165, and if I am short and I don't want to talk to tall people and I only interview short people, what is going to happen is that on average, the average from a sample of everybody that is short is going to yield something, a low value, right? So improper sampling methods can introduce a bias. So we control for this through proper sampling methodology. Another reason why I can observe an unusual outcome is that it happens purely by chance. So I do proper random sampling and I accidentally only sampled netball players. So all of them are tall. So on average, what happens is that the average of that sample is a value quite high under this distribution. It's unusual. It's too high. But that's purely by chance. Now, we also control for this in our hypothesis testing procedure because we incorporate something we call the level of significance or the chance of making a particular error. And we've met that before, and that's called alpha. So we do control for the event of this happening. The third reason for observing such an unusual outcome is that our original assumption about the parameter is incorrect. This forms the foundation of hypothesis testing. So what we're going to do, let me go back to our graph quickly. So let's say I do observe a value over here under the lower tail. And the premise of hypothesis testing is if I observe something so far away from what is expected, perhaps this original distribution is wrong. Perhaps the true distribution is in fact somewhere over here, which will make this outcome that I get more reasonable. And that, all of that is the basis of hypothesis testing. So what we're going to do is we identify areas under the sampling distribution of the null hypothesis that are sufficiently far away from what is expected. If our sample statistic is close enough to the center of the distribution, maybe our original assumption is correct. We cannot prove that it's 100% correct, but it seems reasonable that it is correct. But if our sample statistic is sufficiently far away from what is expected, then we say there is evidence that our original assumption is incorrect. And that is the basis of all hypothesis tests. So how do we do this? What I'm going to show you now in terms of the traditional approach is the basic 5-step procedure, how it works, and I will illustrate this for inference about a single mean. For any hypothesis test, we will start with a null an alternative hypothesis. My null hypothesis, that is denoted H with a subscript 0, is a neutral hypothesis, and it contains what I assume to be true to begin with. This is where our theoretical statistical distribution applies, and that's so we're going to derive the sampling distribution under this assumption. For example, I'm assuming that the average height of the female population is 165 centimeters. So that's my starting point. That assumption could be based on historical information that we've collected from what we've seen from historical information. But things could change in the meantime, but this is a safe assumption to begin with. My alternative hypothesis, denoted H subscript 1, contains the statement to be proven or tested, and it can take on one of three different forms, specifically in the context of inference about a single mean. So I may say in this research that, yes, I know historically maybe it's assumed that the average height is 165, but I think that people in this particular population are getting shorter on average. Or I assume that actually people are getting taller. Or thirdly, I can phrase it as, well, I don't think it's the same anymore. So there are three different forms depending on what I'm testing specifically. We call one of them is called the one-sided test to the right. For example, I want to test specifically if the average is bigger than what I assume to be true. Or a one-sided test to the left, for example, I'm testing whether the average is smaller. So it's very specific, one-sided. I'm not interested in bigger numbers. I'm only looking on one side of the distribution. Or a two-sided hypothesis test where I just say it's not the same as what it was before. That means it could be bigger or it could be smaller. It really depends on what we are testing. In most cases, we will just do two-sided hypothesis test unless it's really important for us to look specifically in one direction. Think of this. If I develop medication to lower blood pressure, then I definitely don't want to see this effect to happen on average. I only want to test for this medication to work. It should lower the blood pressure, not increase it. So I cannot do a two-sided test or a right-sided test for that particular situation. It is so specific that it has to show evidence for lowering the blood pressure. Well, it all depends on what we want to test to formulate the format of the alternative hypothesis. That is our first step. In our next step, we are going to find what we call the critical value. Remember, I said we want to find areas under the sampling distribution that are sufficiently far away to be deemed unusual enough. We do this formally by using our statistical distribution associated with the hypothesis test and deriving the sampling distribution under the assumption of the null hypothesis. And I then make a decision to say, at what level of significance will I do this hypothesis test? What error am I allowing myself? There's always a chance of making a mistake. The default is 5%. You may have heard people talk about this is done at the 5% level of significance. So this is the value for alpha, usually 1%, 5%, or 10%. And the choice of alpha really depends on the seriousness. How much evidence do you need? Or how important is it to make a small error? And I will illustrate this with an example as well. Let's say somebody at the Coca-Cola company decides it is time to change the formula for Coca-Cola. Now, the implication of that is huge. In order to change that, to have evidence to change the formula of Coca-Cola, if you make a mistake there, the consequences are massive. The entire company can go down. So if I'm doing a hypothesis test about that, the evidence that I have has to be extremely strong. In other words, I must make such a small chance of making a mistake. In that case, I will choose alpha very small, 1% or even a lot less than that. But the default is 5%. We will now create our rejection regions, those unusual areas. The critical value depends on the form of the alternative hypothesis as well as my level of significance. And then we identify our critical or rejection regions. So if I do a one-sided test to the left, so I'm testing smaller than, what I'm looking for is an area under the right tail of my sampling distribution that is centered at 0, some or other negative number, and the size of that area is exactly equal to alpha. If I'm doing one-sided test to the right, so I'm testing bigger than, I'm doing the same thing, but I'm looking for an area under the right tail because I'm concentrating only under the right tail area. The size of that area is equal to alpha. A two-sided hypothesis test means I need to look both ways. It's like crossing a two-way street. We need to look both ways. But that doesn't mean I have an alpha percent area under each tail. I take my level of significance, the error that I'm going to make, and I'm going to distribute it under the two tail areas. So the size of each tail area is half my level of significance. Now, I know you're not going to do this necessarily on paper, but just to illustrate what we're doing. So we incorporate our level of significance under this assumption of the null hypothesis, and specifically according to the format of my alternative hypothesis. And I've now identified areas that are sufficiently far away from what is expected for this particular test that I'm doing. This point, we calculate our test statistic. So the test statistic is just my sample statistic calculated from my observed data. I will then go and I will standardize that, create a standardized form for direct comparison with that distribution that links up with the assumption of the null hypothesis. Now, that distribution could be the Z distribution, T distribution, F distribution, or whatever distribution works for that or is a part of the specific hypothesis test. The location of the test statistic under the distribution of the null hypothesis is then assessed in terms of whether this is a likely outcome or not, given our original assumption. Based on where the test statistic falls, we will do the following two things. We're going to make a decision about what to do with our original assumption, and there's only one of two things we do here. We are either going to reject our original assumption or we're going to fail to reject our original assumption. I know some textbooks talk about accepting the null hypothesis to be true. We never accept the null hypothesis to be true because we have not proven something to be true. We can only accept it as possibly true. We can only accept it as a reasonable assumption. So the better way to do this is just to say, do I reject my original assumption or fail to reject my original assumption? And it comes from this. I have identified my rejection region or regions. If I calculate a test statistic, and let's just look at the one-sided test to the right, and I compare that test statistic to this distribution, and it is a value right over there inside the rejection region, that means my test statistic is an unusual observation, and it is unusual enough for me to say that I will reject my original assumption. On the other hand, if my test statistic falls outside of my rejection region, whether it's here or here, doesn't matter where it is, but it's not inside my unusual area, that means it is not sufficiently far away from what is expected for me to be able to throw away my original assumption. So that's the whole premise of what we're doing here. So we make a decision. If the value of the test statistic falls inside the rejection region, we will reject the null hypothesis. But if it falls outside the rejection region, we fail to reject the null hypothesis. We then reach a conclusion in terms of the alternative hypothesis. Remember, the problem that we want to test is captured in the alternative hypothesis, and we were looking for evidence for that to see if there was any evidence for the alternative, yes or no. If I have rejected the null hypothesis, that means that I found sufficient evidence in favor of the alternative hypothesis at that given level of significance. But if the null hypothesis is not rejected, that means I could not find sufficient evidence in favor of the alternative. So we have insufficient evidence. Go back to the courtroom. I assume innocent until proven guilty. If I could not find sufficient evidence to prove beyond a reasonable doubt that the person is guilty, even if the person is guilty, it's just not enough evidence. That means I could not reject the original assumption. Okay, Now, that is the basic structure. So let me recap. We always start an hypothesis testing by stating a null and alternative hypothesis. Then we will find our rejection region or regions under the distribution of the null hypothesis. We then calculate a test statistic from our data, and we compare that with our theoretical distribution. And based on where the test statistic falls, whether it's inside or outside the rejection region, we will make a decision about whether we reject or fail to reject our null hypothesis, which leads to the conclusion of our alternative hypothesis. Now, the way I've structured it here is I didn't even formulate, just in the last 2 minutes, the specifics at each of these points. Those 5 steps are standard for all hypothesis tests that you will ever come across. Depending on the nature of the problem statement, what will change is just the way we formulate the null and alternative hypotheses, because that is specific to the test itself. The rejection region or regions will depend on whichever distribution we're working with. Our test statistic will be a specific formula on how to standardize the sample statistic. Steps number 4 and 5, the decision about the null hypothesis and the conclusion about the alternative, those steps do not change. They follow directly from the procedure of what we have done in our hypothesis testing procedure. None of you are going to go do this on pen and paper. You're going to use a computer. So I'm going to show you the p-value approach and what that is. So assuming that the null hypothesis is true, the probability that the test statistic will take on values as extreme as or more extreme than the observed test statistic is called the p-value of the test. That's a very confusing statement. So let's see if we can explain exactly what the p-value approach is, number 1, and what the p-value of the test is. Effectively, the p-value indicates how far out in the tail the observed value is. The p-value is often referred to as the observed level of significance. It is the smallest level at which the null hypothesis could be rejected. And the smaller the p-value computed from my sample data, the stronger the evidence. So always remember this. The smaller the p-value, the stronger the evidence against the null hypothesis and for the alternative hypothesis. So instead of specifying my level of significance of 1, 5, or 10% up front, all I have to do is calculate the p-value. It is a proportion, or you can express it as a percentage if you want. It's quite easy for us to interpret percentages or proportions. So we just calculate the p-value and we do a direct comparison of the p-value to all the different levels of significance. So the steps involved in the p-value approach are as follows. First of all, we state the null and alternative. That doesn't change. We calculate the test statistic. That doesn't change. But what you see is missing here is creating the rejection region or regions. We don't need to do that. We will use the test statistic to calculate the p-value. And this calculation will depend on the format of the alternative hypothesis. There was supposed to be a bracket over there. And then based on our p-value, the actual number that we get, we will make a decision. So the rule for interpreting a p-value, it's like this. If the p-value is less than a certain level of significance, we will reject the null hypothesis at that level of significance. And if it's greater than alpha, we fail to reject the null hypothesis at that level of significance. Our conclusion in terms of the alternative hypothesis is done the same way as for the traditional approach, or we can just conclude in terms of the strength of the evidence for our alternative hypothesis. And that depends on the interval in which the p-value falls. I calculate the p-value, and it's really small. It's between 0 and 1%, or between 0 and the proportion 0.01. What that tells me is that I've got very strong evidence for the alternative. Remember I said the smaller the p-value, the stronger the evidence for the alternative hypothesis. So a really small value, less than 1%, very strong evidence. Between 1 and 5%, that gives me strong evidence for the alternative. Between 5 and 10% translates into moderate evidence for the alternative hypothesis. And more than 10%, or a p-value between 0.1 and 1, tells me it's weak or no evidence for my alternative hypothesis. So this is a useful summary. I know you will say, but I didn't put equal signs anywhere. And all my years as statistician, I think I've only seen it once where p-value was calculated exactly as one of these bounds. It's usually something with more decimal places, so it will fall in one of those 4 categories. In the next 2 slides, I actually just want to show you what a p-value is. So to understand what a p-value is, let's look at a one-sample z-test for a single population mean. So the one-sample z-test is not one of the ones I explained earlier or looked at the problem statements, but it's similar to a one-sample t-test, but there are more assumptions about what the population variance is. And that is a one-sample z-test for a single population mean. Now, let's say we're testing the null hypothesis. The mean is equal to mu naught, which is some other number. We can go back to our height example and say that number is 165 versus the alternative. We do a one-sided test to the right that the mean is greater than 165. For this particular test, what we are looking for, it's a one-sided test to the right. If we're testing at the 5% level of significance, this is the Z distribution, standard normal, then my critical value is 1.645, and the rejection region is this right tail area of my Z distribution, and the size of that rejection region is 5% of the distribution. This is not drawn to scale, but that's 5% of the distribution. Now, let's say our calculated test statistic is equal to 2. If I compare the test statistic to this graph, I'll see that it's somewhere in there. So it falls inside the rejection region. Therefore, we will reject the null hypothesis. We have found sufficient evidence for the alternative. So what is the p-value itself? The p-value, instead of specifying this 5% upper tail area, I will take my test statistic, and because I'm testing greater than, I will calculate the size of the area, the probability. Sorry, I've got to do this a little bit better. So this area, tail area associated with my test statistic value of 2. In other words, the probability that this curve is greater than the test statistic value of 2, and the size of that area, work it out, and we get 0.0228. So it's 2.28% of this entire distribution. When the p-value is less than my level of significance, what it implies is that the test statistic is in fact inside the rejection region. That's why I can look at this p-value and say, oh, it's greater than 1%, but it's less than 5%. Therefore, it falls within the 5% rejection region. So it's inside the rejection region if I test it at the 5% level of significance. Of course, if I tested at the 1% level of significance, then that test statistic would have been outside the rejection region. So the rule is, if the p-value is less than alpha, it implies that my test statistic is inside that rejection region. Therefore, the null hypothesis is rejected at that particular level of significance. Doing the same thing, same test, but let's have a different value, test statistic value calculated from the sample. So the same scenario, I've got the Z distribution here. I've got 1.645 as my 5% rejection region or critical value. And let's say we now calculate the test statistic and we get a value 0.82. Well, 0.82 is somewhere in here, definitely outside the rejection region, which means I would fail to reject the null hypothesis. There is insufficient evidence for my alternative hypothesis. In terms of p-values, we will calculate the size of the upper tail area associated with this test statistic value of 0.82. In other words, I will calculate the size of this entire upper tail area from 0.82. So it's the probability that the curve is greater than 0.82. When you do that, we see this is 0.2061. So I haven't done this to scale on the graph, but it's to illustrate. So essentially, well, that is greater than 0.05. So if the p-value is greater than my alpha of 0.05, it implies that the test statistic was in fact outside the rejection region, and therefore the null hypothesis is not rejected. So I hope that that helps you a little bit in terms of understanding where a p-value comes from. It is just a very simple and so easy way for us to just say what level of significance, or rather what level of evidence did we find from this particular hypothesis test. Okay, as an example, I'm just using one example here. Tomorrow when I do the Excel workshop, we will do a few more hypothesis tests. And here we're going to do an analysis of variance. Remember, analysis of variance is where we compare 3 or more independent groups with respect to a single numerical variable of interest. So the problem here is the following. The manager at a supermarket chain wants to determine where the product location on the shelf has an effect on the sale of the product. So 3 different shelf locations are considered, the top, the middle, and the bottom. And then we randomly sample 120 stores and randomly allocate 40 stores to each one of those shelf locations. So the first lot of stores, the particular product is placed on the top shelf. For the next 40 stores, the product is placed on the middle shelf. And for the last 40 stores, the product is placed on the bottom shelf. And this is now done for a month. And then the sales of this particular product at each store after 1 month, all of those sales are recorded, and we compare the sales from the stores with the product on the top shelf, compare that to the sales to the middle shelf and the bottom shelf, on average, what is happening here. And we do this with the ANOVA test. Some assumptions, the size and area, display area, the price of the product, all of those are constant across the store, so there's nothing else that could influence this. Furthermore, there are some assumptions of normality and equality of variance for the ANOVA test, and let's assume that is valid for this data. By the way, for the ANOVA, those are the assumptions. There's slight deviations from it. The ANOVA is actually quite a robust test, that if you deviate a little bit from that, it's still a very strong test to use to test this. The null and alternative hypothesis. So this is what we're going to do. State the null and alternative hypothesis. So the null hypothesis says it's neutral. Nothing happened. Same. There's no impact whatsoever. In other words, the average sales of product placed on the top shelf is the same as the average sales for products placed on the middle shelf, and it's the same as the average sales for product placed on the bottom shelf. That means there's no difference, no impact whatsoever. The alternative hypothesis for an ANOVA. Remember when I illustrated the one sample, I said that the alternative can take on one of 3 different forms. For the ANOVA, it's a little different. This is what I like to call a global test. Global in the sense of there are so many different scenarios. So the null hypothesis says that the means are all equal. How could that be contradicted? Well, it's contradicted if at least one of the means is different from the others. There are too many different scenarios. So we are testing they're the same versus at least one of them is different. The other 2 can still be the same, or they can all 3 be different from one another. So it's globally testing this. What I'm not showing you here is how to calculate the test statistic. The computer will do that for you. The distribution we use in the background here is the F distribution. We don't have to worry about that either, because the computer will calculate the test statistic, compare that to the F distribution, and calculate a p-value based on our test statistic. So the program spits out the p-value of equal to 0.016. What is my interpretation of this? Well, if I test it at the 5% level of significance, this is definitely less than 5%. It's also less than 10%, but it is greater than 1%. So if I tested at the 5% level of significance, I would have rejected the null hypothesis. But if I wanted to test at the 1% level of significance, even a p-value as close to 0.01 as this is still, it still implies that the test statistic was outside my rejection region. I like to just interpret a p-value in terms of the strength of the evidence for my alternative hypothesis. So because this p-value is between 1% and 5%, that translates into strong evidence for the alternative hypothesis H1. In other words, I have found strong evidence that shelf location has an impact. And that's the only conclusion at this point that I can make about this ANOVA test. I can just say there's definitely an impact. What the specific impact is will be done through what we call post hoc or multiple comparisons test. It's a secondary hypothesis test. If I have found evidence for the alternative, I need to investigate more and say, all right, what kind of sales? What's the better placement? Is it the top shelf, middle shelf, bottom shelf? Which one is better? And we do that through our multiple comparisons or post hoc test, which is not something I've done here, but this is how you will interpret any hypothesis test p-value. We always interpret it in the same way. Right, so that brings us to the end of the inferential statistics. I don't know if there are any questions at this point, by all means. Well, if there are, please, yes.
There are no questions on the chat so far, and there is no hand that is raised. Just to encourage the participants also that if you do have questions, please, you may raise your hand or you may type your questions on the chat box. Let's take this opportunity to engage with Ms. Smith as much as we can.
Okay, yes, thank you, Koketso. I think
okay, there is a hand that is up.
All right. Yes.
I'll just unmute, enable your mic, and then you can unmute aloud. You may unmute yourself and speak.
Okay, thank you. Thank you, Mrs. Smith, and thank you for the wonderful presentation. My question is the interpretation of the last, the p-value. I didn't get it well. So when we ask to do the interpretation or the report of this example, so how would it be?
Okay, so I want to go back to this slide, and that's why I put this in for you. And I think it may help you when you do your analysis, any hypothesis test. Doesn't matter which hypothesis test you're doing. When we get to regression, you will see we're going to use this table as well. The rule is this: the smaller the p-value, the stronger the evidence for my alternative hypothesis. And remember, the alternative hypothesis is that statement we want to see, do we have evidence for that? That's what we want to test for. So if I have a p-value that is between 0 and 1%, that means it's really small. That gives me very strong evidence. Between 1 and 5% is strong evidence. Between 5 and 10%, moderate evidence, and more than 10%, we can just say, nope, there's not enough evidence here. It's weak or no evidence. Now, this summary I gave you here is all in proportions, and a p-value is always in proportion. Let me go back to this. That's a proportion. If I take that proportion and I multiply it by 100%, I will get a p-value is equal to 1.6%. Now, that 1.6% falls in that category of 1 to 5%. So it's not very strong evidence. It is strong evidence. So our interpretation of a p-value is always take that proportion. If you're more comfortable working in percentages, just multiply it by 100 and then compare it with my p-value intervals. Very strong, strong, moderate, or none. So what people say with this, if I say there's strong evidence for my alternative hypothesis, then I can go back to the way I formulated my alternative hypothesis, and I'll say, what was it? In this case, shelf location has an impact on sales, or at least one group mean is different from the others. In other words, I have found strong evidence in my data that shelf location has an impact. Does that help?
Yes, yes, ma'am. Thank you.
Thank you. And I think there was another question as well.
Yes, we have a hand up from Musa. You may unmute, Musa, and ask your question.
Hello, good morning.
Hi, good morning.
Thank you for the wonderful presentation. Okay, I just wanted to know, how do we determine, or what should inform our level of alpha. How do
Okay.
we determine we are going to use 5% or 10% as our
Okay.
level of alpha? Thank you.
Right. So sort of the default in most analysis, most places will say, I will use a 5% level of significance. So alpha is 5%. We can use different levels of significance, but in most cases, you will see there's probably some indication for your research. I know that, okay, it's not to do with you, Jay, because we don't have medical research, but I know some medical research done at WITS. The students all said to me, nope, we can't do anything at the 10% level. They want 5% level. Right, so that is sort of the standard. Now, maybe at this point, let me just talk a little bit. What is alpha? What is that 5% or 1% or 10%? It's got many names. It's called the level of significance. It's called the error. It's in fact called something, it's called the type 1 error. It's a very particular error that we could make in hypothesis testing. There are two errors, a type 1 error and a type 2 error. Now, the type 1 error is where I incorrectly reject the null hypothesis. So in this particular example, so if the truth is that shelf location has no impact, I could just purely by chance, something goes wrong in the data, I reject the null hypothesis, but actually I shouldn't have. So there's a chance that I make a mistake, that I reject the null hypothesis, but in fact, it is, I shouldn't have rejected. I think maybe with the height of the female population example is probably a better one. So if I assume that the height is 165 centimeters, and then I randomly sample, but I accidentally only sample tall females, that purely by chance, proper random sampling, but most of them are tall, so my average is a bit too high. My conclusion would be to reject the null hypothesis that the average is 165. But that I want to limit the chance of that happening. And that's why if I say, you know what, I give myself a 5% chance of making that error. That is small enough. So choosing alpha, the default is 5%. It only becomes important to choose a different one in terms of the seriousness of making that error. So if you make that mistake of incorrectly rejecting the null hypothesis and the consequences of it is major, such as, let's go back to Coca-Cola example. So the consequences of null hypothesis, keep the Coca-Cola formula, alternative hypothesis, change the formula. If I sample a bunch of people that tell me all to change it, but that's not really a reflection of what's happening in the population, and I then make a decision to reject the null hypothesis to keep the formula, that could have huge consequences, financial consequences on the company. So if the seriousness of making that error is very high, if it's very important to, or it could have huge consequences, then we would go and change our level of significance and make it even more strict, like testing at the 1%. That implies that I must have incredibly strong evidence before I reach my conclusion or decide to eliminate the null hypothesis. But for your research, and I think all of you, it is sufficient to work with alpha as a 5%. Now, what will happen if you then get a p-value of 0.0007, right? We're still testing at the 5%, but now we know how we can interpret p-values. We can look at that and say, you know what? That is so small. That means that my test statistic was really far out in the tail area. In other words, I have found very strong evidence for my hypothesis. What if I get a p-value of 0.051? Well, that's on the border, isn't it? That's just over 5%. Now, what would I do with something like this? According to our interpretation, we'll say that that is moderate evidence. You can even comment on this to say it's not strong evidence, it's moderate evidence. And my gold standard would be to have enough evidence. It must be strong enough. So in this case, a different sample may have yielded slightly different p-value, maybe 0.04999 or something like that. So to get back to your question, for all research done at honors, masters, and PhD level, using the 5% level of significance, there's almost, you don't even have to think about it. You can use that, unless, as I said, the seriousness of making that error is as such consequences that you need to set your level of significance to a lower value. It's not often set to 10%, doesn't happen quite often, but it's just an indication of the level of the strength of the evidence. So I've waffled on a bit too much there, but I hope that answers your question. Okay. All right. If there's anybody else, you're welcome to ask. Then we can move, if not, then we can move on to the correlation and regression analysis. Right. Okay, I think let's move on. And if you have more questions, perhaps we can deal with them at the end. Right, then the regression, correlation and regression analysis. Now let's have a look and see what this is. So researchers often investigate the nature of the relationship between numerical variables to see what kind of relationship it exists, and if it does, how strong is it? Now, this relationship can be modeled mathematically, and then we can use that mathematical model to predict. We do this through correlation analysis, linear regression analysis, and something called the coefficient of determination. And all of those parts will be explained. Now, for prediction purposes, it really is important to correctly identify the roles of the variable within this relationship. Typically, we use variable X and variable Y. Variable Y is called the dependent variable, as its value depends on the values of one or more other variables. The variable Y is also the one we would like to predict based on observed information. Variable X is called the independent variable as it impacts the value of the dependent variable. For example, the sales that a company generates for a particular product may depend on how much the company spends on advertising. So if I spend money on advertising, a possible consequence of that, an influence of that, is that it will impact the sales. Sales not going to impact advertising expenditure. It doesn't work the other way. Of course, if I sell more things, I will have more money to advertise, but the direct effect comes from the effect as a result of spending money. What is the effect on my sales? Another example, the number of hours that students study will have a direct effect on the marks that they get in an assessment. So in that particular case, the hours spent studying will be my independent variable X, and the dependent variable would be the marks or the marks obtained on a test. Right. So for regression analysis, it's important that we know that we define the roles of our variables very clearly. As with all descriptive statistics to begin with, because this at the beginning forms part of descriptive statistics, is that we look at a picture. A picture speaks 1,000 words. So if we want to see if there's a relationship, let's look at our data and we create a scatter plot. It is a visual representation of this relationship between two numerical variables. My independent variable is plotted on the x-axis and the dependent variable on the y-axis. Now, the nature of the relationship could either be linear, either positive or negative. It could be non-linear, or it could be non-existent. So I've got some examples here. The one on the far left, if I look at the scatter plot, there seems to be a bit of an upward linear trend. And it's sort of constant, that linear pattern. Yes, there's a random scatter around the line, but that is an upward linear trend. So it's a positive linear relationship. And the next one, similarly, also capture the nature of that relationship. There seems to be a linear trend and it's in a negative direction, goes down. So the slope is negative. So there's a negative linear relationship. My third graph here, if you look at the points, I can almost join the dots here. This is a perfect non-linear relationship. So ideally, I should not be using linear modeling techniques to try and capture this relationship. There are techniques that are designed for nonlinear analysis. So the linear relationship will not work so well here. There will be too much error. So a nonlinear methodology would be better. Then the last one is where there's absolutely no relationship whatsoever. It's just a random scatter. So the relationship is non-existent. So first of all, I'm going to look at the picture, and then I'm going to go and do some correlation analysis. If there is a linear relationship, I will look at correlation analysis. The degree of association between two variables can be expressed as a correlation coefficient, which is a numerical measure that quantifies the strength of that relationship. There are a number of different correlation coefficients, and it all depends on the nature of the variable. So if I've got numerical variables, I'll do a certain type. If I've got ordinal variables, I can use another type. The most commonly used one is the long name of it is Pearson's product moment correlation coefficient, or just Pearson's correlation. We denote that by lowercase letter r. It's a value between -1 and +1 inclusive. So correlation coefficient, Pearson's correlation, it's a number between -1 and +1. It cannot be outside of those bounds. The objective of Pearson's correlation is this. It measures the strength of the linear relationship between two numerical variables. If I've got a nonlinear relationship, I'll draw another picture. What will happen if you have this wonderful parabolic, perfect nonlinear relationship? My correlation coefficient will say, nope, there is absolutely no correlation here, but there's no linear correlation, even though there is a perfect nonlinear correlation. All right, okay, is that? Let's move on. Now, I'm not going to ask you to go and calculate this. I've only put this formula down because I want to illustrate something. The computational formula for Pearson is the following. In the numerator, to calculate R, we will see the sigma notation. That is just where I sum up values of my variable, either sum of the values or sum of the product. But in my numerator, I've got my independent and my dependent variable, and then the product of my independent and dependent. And it doesn't matter if I do the sum of x times the sum of y, or the sum of y times the sum of x. So it doesn't matter. It's interchangeable in the numerator. In the denominator, under the big square root, I've got two parts, this first term and my second term. The first term is everything to do with my independent variable, and the second term is everything to do with my dependent variable, and we multiply those two terms. So it doesn't matter if I multiply the first one with the second or the second with the first, I get the same answer. What this tells me is that the roles of the variable are interchangeable, and it does not, these roles do not influence the value of R, because if x is correlated with y, y is correlated with x. So it doesn't matter when we do a correlation, we don't need to define the roles of the variable. It's nice to already do that up front, but we don't need to do that because in our calculation, it's not incorporated in that, because if x is correlated with y, then y is correlated with x. Another thing just to note is that my correlation coefficient is sensitive to outliers. I'll give you an example. Let's say I'm correlating the ages of my second year stats student sitting in class with their performance on the exam. So most of my students are like 19, 20 years old. Let's say I've got 5 mature students and all of them are retired and they decided to come study statistics. So they're all over 65. What is that going to do to that sum of X values? It's going to inflate it. So these are outlying observations that will influence the value of my correlation because it will artificially inflate it. Those are outliers, and R is sensitive to outliers. If we have a situation with outliers, maybe we should use a different correlation coefficient, something called the Spearman's correlation that works with ranks rather than with the actual observed values. All right. In terms of interpretation, two variables are positively correlated when large values of one variable are associated with large values of the other, and small values of the one are associated with small values of the other. That really gives me that picture where the slope, the line goes upward. So there's an upward linear trend. Conversely, a negative correlation between two variables implies that large values of the one are associated with small values of the other and vice versa. A correlation coefficient, if the value of the R is closer to 0, it implies a weaker linear relationship, not a weak relationship full stop. As I explained before, it could be a non-linear relationship. It just implies a weaker linear relationship. So when R is exactly equal to 0, there's no linear relationship, but there could still be a non-linear relationship. And I'm also putting this in for you. The value of R is interpreted as follows. It's a number between -1 and +1. So see this as a line. If you start with -1, we've got a perfect negative linear relationship. Closer to -1 is a strong one. Then a bit further away, sort of between 0 and -1 is moderate. And closer to 0 is weak negative. Around 0 is no linear relationship. And then we do the same on the positive side. One of the things you can hopefully see with this is that there is no clear cutoff point to say this correlation is strong, this one is weak. So if somebody interprets a correlation of 0.85 as very strong and the next person interprets that number as strong, both will be correct. They are both correct enough. But nobody should look at a correlation of 0.85 and say that's a moderate correlation, because that's just too far away from it being moderate. Right. So maybe this interpretation will help a little bit in terms of when you do your research and come across any correlation. So that is the correlation coefficient that we can calculate. We now look at our linear regression. Linear regression analysis is a technique used to mathematically model the relationship between variables for the purpose of prediction, specifically where one or more independent variables are used to predict the value of a single numerical dependent variable. Now, what's important with regression analysis is that we only have one dependent variable. We never have more, and not in what you are going to do at all. There's one dependent variable, and I'm trying to predict that thing. And what am I going to use to predict it is either a single numerical independent variable or multiple independent variables. So simple linear regression has only one numerical independent variable, whereas multiple linear regression has multiple independent variables. And here we can have a mixture of both categorical or numerical variables. The main idea of linear regression is to fit a straight line through the data in order to capture or describe the relationship with a simplistic mathematical model. And we really understand this in simple linear regression. Trying to fit a line in a multivariate space is very difficult. So I will illustrate a lot of that just using simple linear regression. So that line is called the line of best fit. Where does it come from? In simple linear regression, in that model, each pairwise observation can be written as a value on a straight line plus a deviation from the line. And that deviation is referred to the error term or the residual. So we have an equation. On the next slide, I've got a graph, and I'll illustrate this on the graph. But here's our equation. Every value on the y-axis is a value on the line plus or minus either a little bit above the line or a little bit below the line, essentially. So every value can be described as a value on a line plus or minus a deviation above or below the line. The equation obtained to describe this linear relationship is called the least squares regression model or equation of y on x. So when we do regression, we will regress our dependent variable on our independent variable. So it's like working backwards. I've seen the effect. Let me go work backwards to see, okay, what happened here? How did that effect occur from x to y? So I am regressing y on x. Our method of least squares ensures that the sum of the squared deviations between the points of that scatter plot and my line is at a minimum. In other words, my combined error is a minimum. That resulting line we get is called the line of best fit. This is the straight line that is closest to all points simultaneously. This does not mean the line is good. It really just means that the line is the best of all possible lines. So our line of best fit doesn't imply a good line. It is just the best one of all possible lines. we now have an equation of that line. So if you cast your mind back to matric, y equals mx plus c. Well, we've got something similar here. As statisticians, we just like to write things differently. Y hat, so that y with a little thing on top, we call that y hat, is a plus bx. So a is the intercept where it cuts the y-axis, and b is the slope, and that's simply the equation of my straight line. And y is therefore the predicted value of my dependent variable on that line. So let's see how it really works. So what we have here is every one of these points has, we'll pick one over here. So this point here has an x value of 1 and a y value of roundabout, let's say 8. So this observed value of this point is where x is equal to 1 and y is approximately equal to 8. So that's the observed value. And that's what we said, that every value, I think I need to illustrate, I'll illustrate it with a different one, is a plus bx plus some error term. So let's illustrate it with this one in this particular point. You will agree with me that this, just erase that, this xy coordinate or value, so the actual y is over here. If I now look at the vertical deviation where x is equal to 3 on the line, and I'll see, well, that yield, that is at a particular y value around maybe, I don't know, maybe 18, let's say 18. The difference here is the difference. So my observed, my actual y value is the value on that line plus this deviation, which is the error term. So every point is the value on a line plus or minus a value, either above or below this. So the whole idea with regression analysis, or the least squares method, what we do here is that we look at all of these vertical differences between every point and the line. And then we square them. These are all the error terms or residuals, and we square them because some are positive above the line and some are negative below the line. So we square them and add all these different individual error terms together. Now, if I take this line that was finally fitted, but let's try a different line. If the line was here, you will agree with me that the difference between this straight line and every point is quite big. There's a lot more. So the error is much more spread around my flat line. So if the line of the least squares model, what it does, it really goes and says, okay, try all possible lines. Here we go. How do we find the one that has the smallest combined error? So my residuals combined is the smallest possible error or deviation from the line that I could get from all lines. This line is then called my line of best fit, and it's also my regression model used to predict my dependent variable, and it's a plus bx, where a is where it cuts on the y-axis and b is the slope. And that's how I get my line of best fit. And again, I'm giving you formulae, not for you to go and use necessarily, because the computer will do this for you, but I want to illustrate something important. Our regression coefficients are estimated through this method of least squares using the following formula. Take note of this. If you look at the numerator, you see something similar to the correlation analysis. I've got stuff to do with the product of my dependent and independent variable. However, what do I have in the denominator? It is my independent variable. It's in my denominator. So it's really important here that the roles of the variables are correctly defined, because if I accidentally swap the roles, I'm going to put the values of y and call it values of x in the denominator, and that gives me a completely different line of best fit. It's a completely different regression model. So it's really important that we correctly identify which is x and which is y. And even in calculating the intercept the order. It's first the independent variable minus the slope multiplied by the dependent variable, dependent variable minus the slope multiplied by the independent variable information. So the order is really important here for regression analysis. Now, how do we interpret the slope? A positive value of the slope means that on average, the values of my dependent will increase as the values of x increase, indicating that positive relationship between x and y. And of course, a negative value of b means that on average, the values of y will decrease as the values of x increase. Why am I saying on average? Because that is what's happening on average. It doesn't mean it happens with every point in my data. I could have a situation with a negative relationship where my y value increases with the x. I could have that, but it's on average for all my data, right? For negative relationship, we then have that inverse relationship. So the sign of the slope will correspond to the sign of my correlation coefficient, because either the line goes up or it goes down. Either the correlation is positive or negative. But the actual numerical values of the correlation R and the slope B are not related. You cannot look at the two and say, oh, okay, it's a small number, therefore it's a small correlation. We do not interpret it in that way. But there is a specific interpretation of the slope, which only really makes sense when you work with data and you understand the nature of your data. It shows the predicted change in the dependent variable for a 1-unit change in the independent variable. So I will say an example. Let's say, what are we going to do? All right. Let's assume that this is my model that I'm trying to predict marks on a test using number of hours that a student will study. And we say there's a positive relationship because the more I study, the more likely I am to get higher marks. What is the interpretation here? My slope coefficient is +2. The interpretation of this is as follows. For every 1 unit increase in x, y is predicted to increase by 2. In other words, for every 1 additional hour studied, I can predict that my mark on the assessment will increase by 2%. This is purely artificial data, so don't quote me on this, but that's just to illustrate the nature of the relationship. What if I had a negative number here? My interpretation would be, for every 1 unit increase in x, y is predicted to decrease by 2 units. And that's how we interpret the slope of our regression model. We can now use our regression model to predict, because the objective of regression is to predict y, but I'm going to add something to that, for valid values of x. Valid values of my independent variable or variables. Now, the x values used to make predictions should fall within the range of the observed values of x, because there's no guarantee that the regression model still applies for x values outside the observed range. Let me draw another picture. So let's say I observe x and y, and it's a nice linear increase, and I can fit a beautiful model, and the points are quite closely scattered around the line, so it's quite a good model. But I've only observed data for x values from, let's say, 1 up to 10, whatever the values are. I have absolutely no idea what the nature of this relationship is for x values greater than 10. As it stands, my line just keeps increasing to infinity. But after this point, it's like you have a big piece of paper over here. We have no idea what the pattern is like. For all I know, it could have a reverse effect. So it's a very different scenario. So this is what we mean with valid values. If I'm trying to predict the value of y using x, my x value must only be a number between the lowest and the highest possible x value observed. We call that interpolation. Any value of x beyond that range, either smaller than the smallest or bigger than the biggest, is called extrapolation. So we are extrapolating this beyond what was observed. The problem with that is that it just becomes more uncertain, because we haven't modeled the nature of that relationship. So the results may not be valid when we do extrapolation. Right. So I said that the line of best fit is the best line of all possible lines, but it doesn't tell me how good the line is. To determine something, to have some goodness of fit measure, how good is my regression model? One of the things we look at is something called the coefficient of determination. It measures how well the regression line fits the data. So it's my goodness of fit measure. It's a simple calculation. Excuse me. I calculate the correlation coefficient and I square it, and I typically express that as a percentage. You can leave it as a proportion, but I typically express it as a percentage. So R squared is my coefficient of determination. And what it does is this. It measures the percentage or proportion, percentage of variation in the dependent variable that can be explained by my regression model. For example, if I have a situation where all the data points lie directly on top of that regression line in a positive direction, then I will have a perfect positive linear relationship. So my correlation coefficient R will be equal to 1 because there are no errors. There are no deviations from the lines to the point. They sit on top of the line. In other words, there's no unexplained variation. My line captures the nature of that relationship perfectly. In other words, my R squared, which is 1 squared times 100%, it will be 100%. Therefore, 100% of the variation in Y is explained by the regression model. On the other hand, if the points are so scattered that my regression model absolutely means nothing, then my correlation coefficient is equal to 0. So it's just a flat line. There's no, it doesn't describe the nature of that relationship because there is no relationship. So in such a case, my correlation is equal to 0. It then follows that my correlation coefficient is equal to 0%. So that's interpreted as none of the variation in the dependent variable can be explained by the regression model. So that gives you the two extremes of interpreting a coefficient of determination. Now, we're quite used to interpreting percentages. We learn how to interpret percentages from a very small age. So the R squared is a very nice measure for us to give us a sense of how good my line is, because we can look at a percentage and say, yeah, that's okay, that's good. Right. One of the things you will, however, note with real data, because there's just so much variability, especially if you observe data from human subjects, that you may end up with a coefficient of determination of, say, 0.4. So only 40% of the variability explained, but within the industry, it may be seen as actually quite high. So you may read some articles where they talk about such a low, it seems like such a low percentage, but actually in the context, it is actually quite good because it's very difficult for us to capture the complexity of systems sometimes. Okay, the value of R squared will be a number between 0 and 100%, or between 0 and 1 if it's a proportion. It doesn't indicate the direction of the relationship. For that, we look at the value of R itself, but it is our goodness of fit of the regression model telling us, is it a good model? Yes or no? Okay, now how do we extend this to multiple linear regression? It's just an extension of the simple linear regression model, and it's widely used in practice as a prediction tool. For example, if I do simple linear regression, one of the examples I had is advertising expenditure. How does that impact sales? But of course, that's not the only thing that can impact the sales of a product. There are lots of things. Word of mouth, product placement, favorability, people's favorability towards the product. There are lots of things that could impact the sales of a particular product. Different forms of advertising, maybe in-store promotions, etc., etc. So in multiple linear regression, the aim is to identify the set of P independent variables that are significantly related to my dependent variable Y. That model is then used to predict the value of Y using valid values of all those independent variables. The form of the regression model is this. I just want to quickly write down the form of the simple linear regression for a comparison. A plus bx, just to keep it simple. A was my intercept, B was my slope, and x was my single independent variable. When I look at the structure here, instead of using A, B, C, D, E, we just use beta or B naught For my intercept, B1 is the slope coefficient or the gradient of variable x1, B2 is the slope of variable x2, etc., up to whatever my last independent variable is. And these slope coefficients will be interpreted in the same way that I interpret the slope coefficient for simple linear regression. We will just add a little sentence to that. So if I need to interpret the slope coefficient B1, I will say keeping everything else constant for every 1 unit increase in x1, y is predicted to change by whatever that slope value B1 is. So you'll see we can look at these coefficients and interpret it all in the same way. Now, it's very difficult for us to model, to visualize straight lines and things like that with a multivariate model like this, but it is just mathematically an extension, and it also uses the least squares analysis. And for that, we just ask the computer to please do it for us. But the modeling process for linear regression, it's an exploratory technique. It's not a matter of just putting the data in and pressing a button and just take the model and predict. First of all, we need to identify and define our dependent variable and a set of possible independent variables. We will look at it exploratory. We'll make a few pictures, a few scatter plots. We'll calculate the pairwise correlation coefficient to see the nature of the relationship. One of the things I will say at this point is you may find that one of my independent variables, when I look at it individually, the relationship between that x and the dependent variable, it may look like no relationship whatsoever. But the moment I put it in a model like this, where I see the combined effect of all the different independent variables, the nature of the relationship could change. So it doesn't make sense to just look at the correlations and say, oh, no, that's not good enough. We also use logic to see what is reasonable. Take the sales example in advertising expenditure. The sales of a certain product. We definitely not going to say that the sales in Gauteng will be influenced by the, I don't know, population distribution or the number of people in a shop in Cape Town. So we're not going to include that information. It has to be reasonable. Anyway, let's move on. Once we've done this, we build the regression model using statistical software packages such as Excel. Excel is not really a statistical software package, but it does have a data analysis component that we can use. But then you have other statistical software packages like SPSS or Stata or R or SAS or whatever. Once I've built the model, I will test the model for goodness of fit and statistical significance. So my goodness of fit measure, here I look at the coefficient of determination, my R squared, and then we have two hypothesis tests that we do here for us to be able to say, is it a good model? We have an ANOVA test, and we have hypothesis tests for each one of those regression coefficients. In other words, each one of those individual slopes. So the B1, B2, B3, etc., etc. Okay. We also need to test the validity of the model. We need to check the assumptions. There are some assumptions of regression analysis, specifically around the residuals. We need to look at the presence of outliers because that can influence a regression model quite severely if I've got a very severe outlier. So there's a whole load of diagnostic tests that you do just to test the validity of the model. Once we're happy, we use the model to predict our dependent variable using valid values of the independent variable. By the way, just before we use the model to predict, if we get to a point and we find that we've got, I tried 5 variables and 3 of them do not have an impact on my dependent variable at all, what I would do is I will start from scratch and only include the 2 original variables. I don't have to keep all 5 variables. But I'll illustrate that again with our example. The hypothesis tests, the ANOVA, this determines the overall significance of the model. The format of the null and alternative hypotheses are given here. The null hypothesis is there's no linear model, so that's a neutral one that says, no, there's nothing going on here. The alternative, well, yeah, there is a linear model, so doing regression analysis is appropriate. For this, what are we going to do? We're going to look at the p-value. It's going to give a p-value. You don't have to worry about the ANOVA table or anything. You look at the p-value. And the p-value for this, we're going to interpret in the exact same way that we interpreted p-values that I showed you before. Compare it to those 5 categories and see the strength of the evidence for the alternative hypothesis. So is it a good model, or is it an appropriate model? Yes or no, essentially. Then the next step is to look at the regression coefficients. So what's important here is if I've got a whole host of independent variables, I want to know the strength of the impact of the significance of each one of those in my model. And we're again going to look at p-values here. The smaller the p-value, the stronger the evidence for the alternative. So let's have a look and see the format of the null and alternative hypothesis. Now, you will note that in my model, I had B's, B1, B2, etc. But here I have betas because inference is always done about population parameters using sample statistics. So each one of these beta i's refer to my regression coefficients, those B's, but in the population context in my hypothesis testing setup. The hypothesis is, the null hypothesis says there's no relationship. In other words, the slope is just a flat line. It's equal to 0. There is no slope. It's a flat line. Whereas the alternative, it's only one form of the alternative. We don't test one-sided to the left or right. We just do two-sided. This is says, oh, well, actually, the slope is not equal to 0. That implies it's either significantly positive or significantly negative. Right. Just a note here about the BIs are the population regression coefficients that are estimated using the beta i's of population, and it's estimating using those BIs in the equation. All of these hypothesis tests, we're going to use our p-value to determine if the null hypothesis is rejected or not, and consequently, if there is sufficient or insufficient evidence for the alternative hypothesis. Let's look at an example. Now, both of these examples that I'm going to show you are based on very small data sets, and I would encourage you not to do small data sets as much as possible. Try to collect as much information as possible. Go read up on sampling and what's more appropriate to use. This is just for illustration purposes. Right. I've got a sample of 10 athletes, and they took a series of tests to measure their fitness. Then the overall fitness score was a number that ranged between 1 and 3.5. So it's just combined together to create some or other numerical value on an interval scale. Now, having done these tests, these athletes then ran a marathon, and their times measured in hours. And then use Excel to create a scatter plot and estimate the least squares regression model to predict marathon time using overall fitness. So it's quite reasonable that the fitter you are, the better you are, or the faster you will run your marathon time. And we can clearly see that is that relationship. So there is a linear trend over here. It's a negative relationship, which makes sense. So if I'm very fit, I'm not going to take a lot of time to run that marathon. But if you're not very fit, parts of the way, I'm sure you're going to walk or sit down. So it's definitely going to take longer. So that's just a visual representation of it. And here I've just taken some or created just the parts you'll see in Excel. This is what it's going to look like. When you do the analysis, there are 3 parts. The one is the regression statistics, the ANOVA table, and the estimate. So let's start with the ANOVA table. There are a lot of numbers here, but what you're interested in is that significance. This comes from the F distribution because that's what's used for the ANOVA. And that is my p-value, which I've just rounded to 3 decimal places. So this is actually a number that is 0.0000 something, but it's small. This is definitely less than 1%. Which means I've got very strong evidence for the alternative hypothesis. And if I think about what is the alternative hypothesis here, in my ANOVA, it was there is a linear model. So I've got very strong evidence that there is a linear model, so doing linear regression is appropriate. Right, that's the first thing I'm going to do. The next thing I'm going to do is say, okay, well, how good is it? So the regression statistics, you see a few things. You see something called multiple R, R squared, adjusted R squared, standard error, and observation. So this is just my sample size. The standard error, well, that's just the standard deviation of my sampling distribution of the estimate. So we're not going to look at that for now. The adjusted R squared, let me talk about the first one first. Multiple R is just the absolute value of my correlation coefficient. In a simple linear regression setting, that's the one we're going to use. It's the absolute value. If I want to know the actual value of my correlation, remember I said that the slope, the sign of the slope and the sign of the correlation are the same. If I look at my estimates, the slope coefficient is negative. So actually my correlation coefficient is minus 0.938. Just so you know, this is what Excel does. If it gives you the multiple R, it takes the absolute value. You get the sign of my correlation coefficient from my slope coefficient, right? Then the next one is R squared, expressed as a proportion. So in this particular case, we can say approximately 88% of the variation in Y is explained by the regression model, Y being my marathon time. Now, what is the adjusted R squared? These two numbers are very similar, but in some cases, you'll see quite a big difference. When we do regression analysis, we don't just throw the book at it and include every single piece of information we can measure. It has to be reasonable, because if we include just everything, we overfit. So the adjusted R squared basically penalizes you for using too many independent variables. So it's got to be, it's got to be reasonable. Okay. But in general, what you're going to work with is the adjusted R squared. So this is a very good model, a very good model fit. We can now look at our estimates. So in terms of the estimates, there are two things you're going to look at. First of all, it's the coefficients part. You can look at the standard error and the t-stat, because all of this is used. This is from the sampling distribution used to calculate our p-value. And remember, for each one of these, the intercept, that is my A in the model, in the simple linear regression model, and the fitness score coefficient is B, so it's my slope. I will interpret each one of these according to that null and alternative hypothesis. The null hypothesis said the coefficient is equal to 0, so there's no relationship whatsoever. The alternative says there is a relationship. We will look at the p-value. The p-value for both of these estimates are less than 1%. In other words, it gives very strong evidence in favor of the alternative. At this point, now I know they're both highly significant. I am not really interested in interpreting the slope coefficient. This is not relevant. I always explain it to my students as this is like the little brother or sister that you just got to hold his or her hand and tag them along. It's just always there, whether significant or insignificant. The intercept's always there because I don't want to force my model to go through the origin on the XY axis to go through 0. So the intercept is always there. It just where it cuts the Y axis, that's fine. We never remove it from our model. What we're interested in is this one, because I want to know to what extent does my fitness impact marathon time. The coefficient is negative. We saw that, a negative relationship. It is highly significant. Therefore, there is very strong evidence for the alternative hypothesis. Oh, I've got a highly significant result. Okay. The beauty of p-values is that I can directly compare them with one another. In this particular case, this all translates into that my fitness score has a very strong impact on my marathon time. And that's how we're going to interpret the output for a simple linear regression. We'll very quickly look at the output of a multiple linear regression. So in this story, a plastics molding manufacturer wants to evaluate factors that could affect the level of percentage wastage from an injection molding experiment. And again, a small sample here. It's only 31 shifts and recorded operator dexterity. So that's how good someone is with their hands. A value from 0 to 30. Higher score means better with your hands. Machine speed, plastic viscosity, and percentage wastage. And then I use Excel again to fit this model. So when we look at our ANOVA, we see that we've got a significant result here. So we've got a model fit, a linear model. Our R squared is 0.65. So 65% of the variation in percentage wastage is explained by this entire model. And then we can go for multiple linear regression. I'm not interested in the multiple R. I only look at the R squared. I can now look at my coefficients. So the intercept, like I said, significant or insignificant is always there. I'm interested in these three variables. So this is less than 1%, this is less than 1%, and this is more than 10%, which means that viscosity has no impact on percentage wastage, but both dexterity and speed have very strong impacts on percentage wastage. The nice thing about p-values is that we can directly compare them. What if, for argument's sake, this was 0.04 instead of 0.001? I can then say that, you know what, both dexterity and speed are significant predictors of my dependent variable, but because the p-value of dexterity is much smaller than the p-value of speed, dexterity has a stronger impact. It is a more significant predictor, a stronger predictor, or a better predictor than speed, but speed is still a significant predictor. So that's the beauty of p-values in the context of regression analysis. All right, so that's how we interpret regression analysis. And that brings me to the end. And I hope we still have a little bit of time for questions. So thank you very much. I think I'm going to stop sharing and then I can go to, if there are any questions, please feel free to ask.
Okay, thank you very much, Ms. Smith, for that very detailed explanation and presentation. I think we have unpacked the inferential statistics and regression analysis concept for us so clearly for us to understand, and we thank you for that. I will then give the opportunity to the participants and the attendees to ask any questions that they might have before we can conclude the session. We have an opportunity to ask the questions. Yes, Akun, I hope I'm pronouncing your name right. You may unmute yourself and speak.
Okay, thank you. My name is Akuen. Quite difficult name.
Akuen, okay.
Okay, thank you for that.
Yes, thank you. My question is, in case of outliers, how would we set or look for it, especially when we see the result after running the process of in the software? So, is there a way that we can detect the outliers, or we have to go back to look for the whole data set, or how? And then if we got some outliers, what the next step? Are we going to continue with the results, or we look for another way?
Okay.
And also for the direction, the negative or positive relationship to where will we, how would we know that if this is negative or is a positive relationship?
Okay. I think I'll start with that in terms of the positive or negative relationship. And that's why we look at things visually. That gives us a clear indication. And of course, in our model itself, if my coefficient is negative, then it indicates a negative relationship. And if the coefficient in the regression model is positive, it indicates a positive relationship. So from the output of your model, you will find positive or negative coefficients, and that will imply positive or negative relationship. However, on that, I just want to say that let's say you have a negative coefficient for a slope, but it's not significant. Well, then you can say that that negative number is approximately equal to 0. So we'll only interpret it as a positive relationship or negative relationship if we have a significant predictor. But that comes from the model. One other thing on that is that you will it's important you understand your data. When you look at the relationship, let me take that marathon example. If I saw a positive relationship, that wouldn't make sense, isn't it? So in other words, the fitter you are, the longer you take to run. So we must always be critical when we look at our data and look at the results, that it actually makes sense in the context of what we have collected, the data that we have collected. So that's in terms of the nature of the relationship. In terms of the outliers, outliers can really cause a problem. So sometimes we can just spot an outlier by looking at the scatter plot to begin with. And then if there's one extreme outlier, then it's probably better to remove it up front. But as part of the regression analysis modeling, exploratory modeling process, there are diagnostics built in that will specifically for outlier detection. So there are quite a lot of different ones that will identify the outliers in either the dependent variable or the independent variables. And what we would typically do with that, if something is very extreme, then we can remove that observation. Of course, we don't want to delete our data, but we can remove that observation. The problem is sometimes that once you remove one thing, you actually the model shows other outliers. In some cases, we do transformation of our variables, or we add additional information to see if we can counteract that effect. So it can get quite messy sometimes, but it's in general, if you have a few outliers and they're not too extreme, that may be okay. But if it gets really bad, then perhaps regression is not the appropriate method to use. Then maybe some other non-parametric tests would be better. There are other multivariate modeling techniques that can be used as opposed to a regression analysis, especially if you do have a lot of issues with outliers in your data. So I hope that helps.
Yes, thank you.
Anybody else?
Any other questions? Okay, let's make use of this opportunity to engage with Ms. Smith. Just a reminder to everyone that there is a feedback survey on the chat box. I'll post it again for the last time. Please, can you complete the feedback survey before you leave the session today? And also, you may also suggest some of the topics that you want us to cover on the feedback survey. And also, this will ensure that you get the certificate of attendance. So please, can we complete the feedback survey before we leave the session? And just the final round, are there any other questions?
I think I've
Okay.
overwhelmed everybody with a lot of information here, but I will make this presentation available anyway. Kukita, I will send it to you. And yeah, so perhaps just have a look through that. And then when you focus on whatever you're going to do, I think at the end of the day, what you have to take away from this, especially from the hypothesis testing, at the end, what you're going to do, you're going to do a hypothesis test. You're going to end up with a p-value. And if you know how to interpret that p-value, link it back to stating the null and alternative hypothesis, then you're in a good space. You know what it means. And actually tells you the result of what you're getting. Okay.
Of course. Thank you. Thank you so much, Ms. Smith. So on that note, then we will make the final remarks for this workshop. I hope that everyone got to understand, the inferential statistics and the regression analysis. And we also got to understand the p-value, where it comes from and how you get to accept or reject a hypothesis, which is very useful for us. And definitely we will keep on referring to this recording and the slides as we analyze our data, and that this will help us a lot. And of course, I will share the presentation slides with everyone, and the recording also will be uploaded on our module communities and the RCDMS. So on that note, if there are no more questions, please allow me to thank all the attendees for taking this time to join us today and engaging with Ms. Smith. And also, please allow me to also thank Ms. Smith for the very detailed presentation. These concepts were thoroughly unpacked for us to understand, and we truly appreciate you preparing and giving this presentation and honoring our invitation to come and present with RCD. Thank you very much. And just a final reminder to complete the feedback survey. And on that note, have a good day further. Thank you.
Thank you, everybody, and good luck with your research. All the best. Yeah, all take care.
Thank you.
Bye-bye.
Bye.